Okay, in this lesson we're going to talk about graphical transformations. We're going to take the basic functions that we've already studied this unit and we're going to apply some transformations to them and graph them by hand and see what each transformation does. So starting off with an example, we've got a function g of x equals x squared minus 3. First thing we want to do is we want to identify what parent function is this function based on. So what's the most simplest form of this type of a function? So we've got an x squared, so this is definitely a quadratic function. So let's start there. Let's graph our parent function. Alright, so we've got f of x equals x squared. We've got our some 5 key points. We've got our parabola with those 5 points graphed. So let's start there. So let's put that on our graph down here. Okay, so there's our y equals x squared. So we're going to start off with our parent function. Next thing we're going to do, let's plug in these values in and see what happens to our y values, or our g of x. Okay, negative 2 squared is 4, take away 3 is 1. So we've got a point at negative 2, 1. Negative 1 squared is 1, minus 3 is negative 2. We've got a point at negative 1, negative 2. 0 squared is 0, minus 3. 1 squared is 1, minus 3, negative 2. And 2 squared is 4, minus 3 is back to 1. Okay, so there's our 5 key points. We get the overall basic shape from those 5 points. And we've got our parabola. We've got our g of x graphed here. Now this is where colored pencils, highlighters, colored pens really come in handy when we're graphing these transformations by hand. So we can tell the difference between our parent function and our final function. So let's see what's happening to our values here. Now this x squared minus 3, notice that our final graph looks like our parent function. It's the same shape, the same size, the same orientation. The only thing that changed was its location. So it shifted down 1, 2, 3 units. So we can look at each of our points on our parent function, shift each point down 3 units, and get to x squared minus 3. Okay, let's look at another example. So here's g of x equals 2x squared. Again, we've got a quadratic function. Start with our parent function's graph. That's y equals x squared. Now in our table, let's see what happens when we plug in the same x values from our 5 key points. So negative 2 squared is 4 times 2 is 8. Negative 1 squared is 1 times 2 is 2. 0 squared is 0 times anything is 0. 1 squared is 1 times 2 is 2. And you can see the symmetry here. 2 squared is 4 times 2 back to 8. So let's plot these points. We're at negative 2, 8. We've got positive 2, 8. We've got negative 1, 2, positive 1, 2. And 0, 0 again. Okay, if we fill in the overall shape of our parabola, then let's see what happened here. So it didn't shift any, but it looks like it was actually looks like it was squished from the sides, like it was compressed. But what really happened was that we had a vertical stretch. So we took each of our points and we stretched our y values by a factor of 2. So notice if we compare our y values from our parent function to the ones in g of x, 4 times 2, 1 times 2, and so on. Okay, that's exactly what that 2 does. So each of those y values was stretched vertically by a factor of 2. Another example. G of x equals negative x squared. Again, we've got a quadratic, that's our parent function. We graph it. And let's fill in our table. Negative 2 squared is 4, but then we put that negative in front. Negative 1 squared is 1 with a negative. 0 squared is 0. Who cares about a negative? 1 squared is 1 with a negative, and we see the pattern. So let's plot these points. Negative 2, negative 1, 2, 3, 4. Negative 1, negative 1. 0, 0. 1, negative 1, and 2, negative 4. All right, let's fill in the rest of our parabola. And notice what happened. Same size, same shape, but the orientation is different. It looks like it flipped over the x-axis. That's exactly what happened. That negative in front took each of our y values, and if they were positive, it made them negative. So it, in a sense, reflected it over the x-axis. All right, another example. G of x equals x minus 3 in parentheses squared. Okay, now, notice the difference between these two equations. The g of x in green and this one in blue. The minus 3 is on the end on that one. The minus 3 is inside the parentheses in this guy here. Okay, in this one we shifted down 3. In this one, let's see what happens. Okay, so I've kept my same y values in this table. Now I want to see what x values will give me the same y values. All right, so if I want a y value of 4, like this point here, then I want some number squared to get 4. That number's got to be 2. So what minus 3 gives me 2? Well, let's see. 5 minus 3 gives me 2. So if I do 5 minus 3, that's 2 squared. Okay, so I've got a point at 5, 4. If I want 1, then I want some number squared to give me 1. So I want this to be 1. What number minus 3 will give me 1? 4 minus 3 is 1. 1 squared is 1. So I've got a point at 4, 1. Okay, if I want 0, I want to square 0. So 3 minus 3 is going to give me 0. Okay, and I'm sure you see the pattern. If I want 1 again, then could I plug in a 2? 2 minus 3 is a negative 1. Negative 1 times itself is a positive 1. I like it. And we can infer that the next x value is going to be a 1. So we've got a point at 2, 1, 1, 4. Plug in that 1 just to make sure. 1 minus 3 is a negative 2. Negative 2 times a negative 2 is a positive 4. All right, so there's our parabola. Graph it. Okay, looking at our g of x. This is our f of x, or our parent function. Same size, same shape, same orientation, but the location shifted to the right 3 units. So each of these points shifted right 3 units. Okay? Let's look at this guy. Okay, in purple, g of x equals 2x in parentheses squared. Notice the comparison between these two, notice the difference. We've still got a 2 coefficient, but this time it's inside the parentheses, it's being squared along with the x. Alright, so we've got our same y values. Let's see what we can do to get some different x values with the same y values. Okay, if we want 4 again, we want 2 squared. So 2 times 1 is 2. 2 squared is 4. So I've got a point at 1, 4. Okay, if I want a 1 y value, then I want 1 squared or negative 1 squared. So I can do 2 times 1/2 to get 1. Or I can do 2 times negative 1/2. That'll give me a negative 1. Negative 1 squared is still 1, so I might put that down there. I've got 1/2, 1, negative 1/2, 1. Okay, if I do that same method to my 4, I can also get a 4 by squaring a negative 2. So if I do 2 times a negative 1, I've also got negative 1, 4. And 0 squared is 0. 2 times 0 is 0, so I've still got a point at 0, 0. Okay, so a similar graph. We said on this one that it looked like it was a horizontal compression, but it was actually a vertical stretch. This one is actually a horizontal compression or horizontal shrink by a factor of 2. So when that 2 is on the inside of the parentheses, what we really did was we stretched it by a factor of 1/2. We took all our x values. If you compare the tables from our parent function to our g of x function, all of our x values are half of what we started off with. Our y values stayed the same. So on our graph, we could keep all our y values of our plotted points and just take half of those x values and plot our new points. All right, one more of these. Let's see, what are we going to do with this guy? Stay. Okay, we got g of x equals, in parentheses, negative x squared. All right, so if we start plugging in some values, we've already got our parent function graphed. If we plug in, let's say 2, the opposite of 2 squared is still 4, so we've got a point at 2, 4. If we plug in a 1, negative 1 squared is still 1, so 1, 1. If we plug in a 0, we're going to get 0 out. And you see the pattern. The opposite of a negative 1 is a positive 1 squared. Opposite of a negative 2 is a positive 2. Squared is 4. And it looks like we've got the exact same function. So a quadratic function isn't the best one to illustrate this transformation. But what's really happening is we're reflecting our graph over the y-axis. Now, since our parent function x squared is an even function, we can't tell the difference because we're just folding it over onto itself. Because it's even, it doesn't look any different. But if we had, for example, a cubic function, look something like that, and we were to, if this is y equals x cubed, and we wanted to graph y equals, in parentheses, negative x cubed, then it would flip over our y-axis, so this 1, 1 point would be here, and it would look something like that. All right, moving on. So let's summarize all of that information that just took a long time to go through. All right, here is our standard form, our vertex form equation expression for doing transformations by hand. We've got a times f, where f is our function, of b times x minus c plus d. Now, again, if you got colored pens or pencils, try to color code it. You'll see why. All right, we've got a nice little table here. We've got inside and outside transformations, and we've got pluses and minuses, multiplication and division. Okay, let's start here. If we have f of x plus c, so if we're adding a value directly to that x, then what's going to happen is we're going to shift that number c units to the left. We're adding a positive number. Okay, if we're subtracting a positive number, we're going to shift to the right. Weird, right? Subtracting, you think to the left, but the inside values are the opposite of what you think would happen, of what's intuitive. Okay, let's keep going down this column here. If we have f of b times x, so if we have some coefficient in front of x, then that's going to be a stretch or a shrink horizontally, and it's going to depend on what our b value is. If it's less than 1, it's going to stretch it. If it's greater than 1, it's going to shrink it or compress it. All right, if we have f of negative x, so if we have a negative directly affecting that x variable, then it's going to reflect over the y-axis. Kind of you can think of it as a horizontal reflection or turn. Another way to look at these is kind of like a composition. If you had a parent function and then you took f of x minus c of that function and you plugged in x minus c into where that x was, then you can think of the transformations in that way, kind of connecting back to our f of g of x and our inverses and those kind of compositions. Okay, let's look at this column. Variables or transformations that affect on the outside of the function. Okay, so if we have our function f of x and then we've got plus d on the outside. Okay, so not directly affecting the x, but just kind of tacked on the outside, then we're going to shift d units up. D is positive. And if we subtract d, or if d is negative, then we're going to shift that many units down. If we have a coefficient in front of our function, so our a value, then we're going to stretch or shrink vertically. So if that number is bigger than 1, then we're going to stretch it by that factor. If it's less than 1, we're going to shrink it by that factor. And if we have a negative in front of our a value or in front of our function, then that's going to reflect our whole function over the x-axis. Okay, good to know this stuff. We're going to be doing this to each one of our functions, not just quadratics, but this works for all of our basic functions. Okay, so real quick, let's look at another example of a different function besides quadratic. If we're asked to graph g of x equals square root of 5 minus x by hand using transformations, okay, we're going to do this one step at a time. Let's start off by identifying what our parent function is. I see my radical, my variables underneath it, so I know that my parent function is our square root function. Okay, so starting there, so I want to start off by graphing that on my coordinate plane. Okay, I'm going to make a little table of values. Remember, we can't plug any negative numbers in here because we can't have negative numbers underneath the radical on our real number coordinate plane. So let's start at 0. Let's maybe do 0 through 3. Okay. Square root of 0 is 0. No, scratch that. Square root of 1 is 1. Let's make this a little easier. Let's pick our perfect square so we don't have to mess with decimals or fractions. Square root of 4 is 2. Let's pick our next perfect square, 9. Square root of 9 is 3. So there's 4 points from our parent function. Let's plot those on our graph. 0, 0, 1, 1. 4, 2, and 9, 3. Okay, so that's our parent function. Start off there. Again, if you have colored pens or pencils, now's a good time to use them. All right, so next step, now that we've found our parent function and graphed it, is I want to make sure that my function is in standard form, that standard or vertex form that we just looked at on the last slide at the top. Okay, right now it's not. Let me write it just to compare it. Okay, so it's not in this form. Now, there's no radicals in this expression or this function here, but that's where my f of x comes in. That's my function, that radical bracket. What's different is that in here I've got x minus c, here I've got some number minus x. So I want to rearrange that. I want to use this commutative property to make it look more like this. So next step, my g of x is going to be, I'm going to switch these two around. I'm going to put the negative x first, 5 is positive. Okay, commutative property of addition says that that's fair game. The next thing I want to do is, in our standard form, we can't have a negative right inside of this parentheses here. So I want to factor out that negative 1. Okay, so I factored out that negative. Now I've got x minus 5. If we forget to do that, we're going to be shifting in the wrong direction. And our final graph is going to be off. So now it looks more like this. I've got an x minus, again, it could be plus, but x minus 5 in this case. My b value is a negative 1. C value is 5. All right, let's graph this. Let's take it one step at a time though. So when we graph by hand using transformations, and we've got more than one transformation happening, take it one step at a time. We're going to have several different functions graphed on the same graph, but as long as we use different colors or we make certain ones stand out, then it'll all be all right. So first one I want to do is this b value. I want to kind of do my transformations from left to right on my function. This b value we saw in our table is a reflection over the y-axis. So we're going to take our function and we're going to reflect it over the y-axis. So I'm going to graph this equation. I'm just going to apply this transformation first. Okay, so reflecting it over my y-axis, 0, 0 stays the same, 1, 1 becomes negative 1, 1. 4, 2 gets flipped over, becomes negative 4, 2. 9, 3 becomes negative 9, 3. Okay, and there is my equation, y equals square root of negative x. Equivalent to that. Okay, so we reflect it over the y. Next step is to take that equation and do our next transformation. Okay, so this next guy is going to be negative 1, and then we've got x minus 5. So this is our g of x function. Okay, this transformation here is a shift to the right 5 units. So we're going to take our pink function here and take each point, shift it to the right 5 units. So this guy, 1, 2, 3, 4, 5 goes there. This guy, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 0, 0 becomes 5, 0. And we have our final g of x function. So if you're just using a pencil, you don't have highlighters or colored pens or pencils, make that bold, label it with g of x, make it stand out so that on a quiz or a test or on homework or classwork, if I'm looking at it, I can tell which one is your final function. All right, we got one more example. If I can find it. Here we go. Let's say that I don't give you an equation for a function, but I still want you to graph it using transformations. So this example, we want to perform the following transformations given f of x. Here is our f of x. We don't have an equation for it. It looks kind of funny. We've just got a graph. Can we still do transformations without an equation? Absolutely. Let's start with this guy. Okay, let's say we want to find f of 2x plus 6 of this function here. This is our parent function. So first thing we want to do, we've already got our parent function, so step 2 is we want to make sure that it's in standard form or vertex form. We can't have a coefficient right in front of that x there if we're adding a number, so let's factor out that 2 and we get f of 2 times x plus 3. That reveals our shift, and we've got a stretch here, okay, or a shrink. So we've got a horizontal shrink by 1/2. Remember, with the things that directly affect the x, it's kind of the opposite. So we take the inverse of that b value. If we start off by graphing our parent function in black here, if we just do the horizontal shrink, we get our graph in blue. So our x values get cut in half, our y values stay the same. So this point, -2, 4, we keep the 4, take half of that -2, and we get -1. Do that with each of our points. The next transformation is that plus 3 to the x. That's our, let's see, a, b, c value. So we shift left 3 units since we're adding a positive. We take our blue graph, each of those points, shift to the left 3. Okay, our answer is in purple. You can label that by putting the function name on it, or color coding is super. All right, let's look at one more example. Okay, let's say we want to graph, again, using the same parent function, -2 times f of x over 3. I want to rewrite this to look like my standard form. We already know our parent function, so that's going to be -2 times f of 1/3 x. Okay, that kind of brings out our b value. If our b value is 1/3, it's going to be a horizontal stretch by 3, but we've also got a vertical stretch by 2, and this negative gives us a reflection over the x-axis. All right, so on our graph, we start off with our parent function in black. Let's do our transformations one at a time, left to right. First one, reflect over the x-axis. So all those x-coordinates stay the same, y-coordinates become opposites. So our graph in blue. Next, we want to take that blue graph and stretch it by a factor of 2 vertically. So keep our x values, y values get doubled. So that 1 becomes 2. This -4 becomes -8, so on. And then one more transformation. If we take that purple graph, stretch it horizontally by a factor of 3, take the reciprocal of that b value, then we're going to be taking those x values, multiplying them by 3. So this x value of -2 multiplied by 3, keep our same y, our same height, multiplied by -3 becomes a -6. And same thing with each of our other purple x values. So our final graph is in green. We've noted that to the side. And that is graphing transformations by hand.